Okay, now I just constructed the ellipse. I started with the rectangle. Look like this. Cut the rectangle in half horizontally and vertically. I marked points here, 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 and here, and I sketched tangent to this line at this point, tangent to this line at this point, etc. And I got something that looked kind of like this. The one I did over there was better. But there it is. Okay. That's how you sketch it. Start with that rectangle. Any conic section, you start with a rectangle. If you want to draw it reasonably well. Okay. Now, if the center lines coincide with the X and Y axis, this thing has an equation. Somebody started to tell me. Okay, now the first answer I got was how you write the equation. This way you can write it with parametric equations. Okay. First of all, that would be it. Now that's in the chapter you should be reviewing. Because you really want to know that. That's real important. Okay. Now we're going to talk about quadric surfaces today. And not the parametric equations, but I'll just riff on this just a little bit. You could write R equals A cosine of theta of T I plus B sine theta of T times J. So that the velocity would be the derivative of this, which is theta prime of T. Make sure that prime is visible. Okay. And you also have an acceleration vector. So this tells you your direction and magnitude of your velocity depending on your theta of T function. Theta of T might be a linear function, it might be 2 pi T. So you go around this thing in 1 unit of time. Okay. Could be pi over 2T, so it takes you 4 units of time to get around. Could be T squared, in which case things get a little weirder. Okay. If it was T squared, it would take you the square root of T, square root of 2 pi units of time to get around. So you kind of want to store that whole idea away because that's the next chapter, which is coming up real quick. Okay. So that's important. Now, as applied to what we want to talk about today, which is quadric surfaces, it's not as important, but it can be connected. Still, we want to get the shapes and sketches of quadric surfaces. Okay. So that's a good answer. Not the one that I was fishing for, but sometimes you go fishing and catch something you weren't expecting. Okay. What I do class, that's what we do. Okay, so that's what we got. Yeah, that was a very good answer, very good observation. Okay, now, just an equation in X and Y. Anybody know what the equation this ellipse would be in X and Y? Well, that's the equation. Okay. If the center is at the point HK with no rotation, so that this is no longer the x-axis, this is no longer the y-axis. This is the point HK. This distance is still A, this distance is still B. Well, then you simply shifted the position of this thing, H units in the X direction and K units in the Y direction. So the equation, if you remember transformations from pre-calculus, incidentally, I digress for a second. I picked up an old graduate school book that I'd had for 50 years and still trying to understand the thing because it's pretty advanced. Okay. That's semi-research level stuff. And I was reading it and saying, gee, if I'd had a really good pre-calculus course, the very first thing we saw was a rational function with complex number coefficients. I understood the analysis of it because I understand complex analysis fairly well. But I thought, when I was first learning this, when I was first looking at this, I had a deficiency from pre-calculus because I never had a pre-calculus course. So I didn't really understand rational functions with real numbers, much less with complex numbers. Just saying, I think some pre-calculus that we really ought to be teaching better, and they really ought to review pre-calculus once in a while, because it really helps. If you run into stuff you're not sure, okay, this is just translation to coordinates, which you should understand because it's really kind of important. And you can make sure you understand why that is. Okay. You replace x by x minus h, that translates every point, h units in the x direction, and similarly, y minus k. Okay, that's an ellipse. Now, what are the conic sections? What's another conic section? Okay, got a good answer. I asked about what are some of the conic sections? Somebody said a hyperbola, which is good because that's the next one I want to draw the same picture. Okay, except we do something different with it. Now, what are the conic sections? Got the answer. You take two cones, one upside down. Well, that's really just one cone. It kind of goes like this. Okay, kind of. Its reflection is part of the official cone. Okay. But for building a conical structure, we don't build both parts. Okay, we stop at the apex. So I do, well, it's all right. So you got this cone. It's a double cone if you wish. Okay, slice it with a vertical plane, you get a hyperbola. Okay, wait a minute. Take that back, I'm lying, you got a hyperbola. Okay, slice it this way, you get a circle. Slice it this way, a little up from the circle, but not so up that you match the slope of the cone, and you get an ellipse. Okay. Now go a little further, what do you get? Okay. And so forth. Well, we can picture that. But that's where these things come from. So you have three possibilities. Okay, now to draw a hyperbola. You draw the ellipse like this. This is still A. This is still B. There are two hyperbolas in this picture. It's one of them. You get one of them. You put the vertices here and here. And you start out tangent, and then you approach this line as an asymptote. And do the same thing over here. There's one hyperbola. Or start here. There's another hyperbola. Has two sides. Okay. Um, the equation of the hyperbola, well, plus or minus x squared over a squared minus or plus y squared over b squared equals 1. Right? Now, in other words, if this is plus, this has got to be minus. If this is minus, this has got to be plus. Okay. So let's look at both cases. Which one is like this? Okay. Would the x squared over a squared be positive or negative for this one? Well, the one thing you see is that for this hyperbola, x can't ever be 0. You know, it never hits x equals 0, assuming that, again, this is the x-axis and this is the y-axis. Okay. And x can't ever be 0. So in which case would x never be 0? Would it be okay? So for the green parabola, x is never 0. Which one of these equations forbids x from ever being 0? Well, if you put x equals 0 in here, well, if you put x equals 0 in here, what do you get? You get y squared over b squared equals 1, right? Anything wrong with that? Could y squared over b squared equals 1? Yeah, y equals b or y equals negative b, right? What if you put x equals 0 in here? You have negative y squared over b squared equals 1. Well, y squared over b squared is a positive number. So you have a negative number equals a positive number. It can't be. That makes sense. So that's this parabola. And this parabola, y is never 0 here. And if you let y equal 0 here, you get something impossible. Okay. Now, okay, so we had the comment. Well, if you let x or y, whichever the case, be a multiple of I square root of -1, make a complex number out of it, sure. But if it's a complex number, you can't divide it, you can't graph it in a real plane. We're talking about real parabolas and hyperbolas. And I once knew a whole lot about the complex variables. So I probably teach you how to do that in a year. But yeah, y'all are really bright. But we don't take time to do that. Okay, so there it is. There's hyperbole, right? Okay. Now you have this stuff about vertex and directrix. And you can do vertex and directrix with ellipses and hyperbolas. And you can do it with parabolas. I'm going to leave parabolas. No, I'm writing something down stupid here. Be my mistake. Okay. Thinking, I got pre-calculus in my mind. I wouldn't have done that with them yet. Okay. So that's your parabola. And of course, the limiting value, the limiting case of a hyperbola is two straight lines. Okay. And that's basically where A and B both approach zero, but in some ratio. So we're not going to talk too much about that. I want to just give you that much of, you know, how you sketch these things. Sketch a parabola. In a box, of course, it goes outside the box. Divide the box in half, vertically and horizontally, then divide this in half. And you divide this in half, then divide this in half, divide this in half, divide this in half, divide this, divide this, divide this. Move over one, down two, over one, down two, down to here, up to here, up to here, and you don't have to use numbers there, you can picture the problem. You look what I'm doing in pre-calculus, pretty easy. Okay. But I'm not gonna define it. It has that shape, and you can draw it any way you want to, except that much of it is sketched by hand. So this can be used. If you just use this point, this point, this point, this point, this point, without using these points here, you're probably going to screw up the shape of it down near the blunt tip. Okay. But you can still get a reasonable representation. And if you know what it looks like, you get away with it. Okay. Now, running the board space here. Get y'all working on something. Doing the washing. I'm not sure I'm using the same letters. But this is not quite a general quadric. This defines what we call a quadric surface. This particular quadric surface, the axes of all the parabolas, hyperbolas, ellipses, whatever, would be parallel to the coordinate planes. Okay. I need more. We're in three dimensions. It's a general quadric form. Looks like this. Okay. That's just a function of X, Y, and Z. We could even say, okay, this is a function. It's three variable. And when we write this, that means that X, Y, and Z are considered variable. The other things are constant. Now, Z equals 0. Getting in my way. Hang on a minute. I'm still getting in my way. Go on. Okay. Make sure everything's on board. Okay. If this equals 0, then this thing becomes a little bit simpler, right? That should be Vx. We get this. Now. Not gonna be A. I'll use alpha. We can complete the square on X and we're gonna get X minus something squared. Okay. In the something, we divide through by, we get B minus A here, so we square half of B minus A, we get B squared over four A. So we're gonna have to add B squared over four A to the end, okay? Then we get a perfect square, and H would be over two A. Yeah, but you write it out. It's simple enough. You remember how to complete the square, and you should. If not, it's easy enough. You learn that in algebra 2. Okay. Then you learn it again in pre-calculus. Then you use it in calculus to do like rational intervals. Okay. So you should have done a decent amount of completing the square by now. So you can do it, and you might have to. Maybe not. I don't remember. I haven't looked at the problem since I closed it. Okay. There we have it. Now, this could be then. No, I don't need H1 and H2. Just call that H and K. I don't know why it wasn't mentioned. And so call this H. Call this K. And this would be over quantity gamma over beta equals 1. And what's that? Well, if alpha and beta are both positive, it's an ellipse. If one is positive and one is negative, it's hyperbola. Okay. And it centers at HK. And now you can sketch it. Let's assume that H1 and K, that H and K are both 0, because that'll be the case for most of the quadratic surfaces you see. And if you can do the quadratic surfaces where H and K are both 0, then you can shift it anywhere you want to. What we're going to get would be one of 3 possible things. Okay, first of all, this distance here would be the absolute value of gamma over alpha, because that should be like x squared over a squared, right? This would be x squared over a squared, y squared over b squared equals 1, maybe plus, maybe minus over here. So you get maybe a hyperbola or maybe an ellipse. If they both end up negative, then you got nothing. So this is like A, but of course, we're using A up here. I can't really use it. Maybe should have used capital letters up there, as your book does. Okay, this distance here is the absolute value of the square root of gamma over beta. Now, why absolute value? Because A, B, C, D, E, F, and G, and H, I don't have H, all these letters could be, stand for any real number, positive or negative, right? Okay. So if, when you complete the square, alpha, beta, gamma, any of those could end up positive or negative. So that gamma over alpha, gamma over beta could end up positive or negative. If it ends up negative, then we're going to have a negative sign over the, and then this over the absolute value of this thing, right? That makes sense? We can end up with positive and negative. This could be positive or negative. This could be positive or negative. Okay. Then we have the same rectangle problems. Now this assumes that A and C coefficients of x squared and y squared are both non-zero. If one of them is zero, you end up with a hyperbola, which is pretty simple. Okay, so I'm going to deal with ellipses and the two possible hyperbolas, so that what we would get down here in the xy plane might be an ellipse, might be this hyperbola, might be this hyperbola, just depending on how the signs of gamma over alpha and gamma over beta come out. Remember that alpha, beta, and gamma just stand for whatever coefficients we get here. You know what? I didn't need alpha and beta. Could have called these A, B, and couldn't call that C. Let me back up a second. If I complete the square on AX squared plus BX, I'm going to have coefficient A to get an AX squared when I square this, right? So kind of a bonehead thing I did by using alpha and beta. I'm going to change my alphas and betas to A's and B's. What I did wasn't incorrect, but it turns out that alpha is going to equal A and beta is going to equal B. So there's no point in introducing my point was I didn't want to confuse this with the A you have for x squared over A squared and y squared over B squared. But so A is now instead of the A for your ellipse or hyperbola is the square root of gamma over A, where A is the number you have here. So that might be a little confusing, but you can see that if I let Z equal 0, I'm going to get this. Okay. So I'm going to have one of these three shapes when I end up completing the square. Or maybe I end up with nothing at all in the XY plane. That could happen if this and this end up both positive, this ends up negative. Okay. If these are both positive, then all this is positive, and that can't be negative. Or 0. Yeah, there's a minimum you can have given your parameters. Okay. Okay, well, the point of this then is that now we don't know what the set of all X, Y, and Z values are that satisfy this equation. But we do know that if they're in the XY plane, it's one of these three shapes in that plane. Got a question, I probably did some other bonehead thing. Okay, somebody said, that should be C, shouldn't it? Yeah, that's what's in front of Y squared, okay? So again, I was careless when I wrote down B. Okay, now the whole point of this is you can let Z equal 0, you can complete the squares, and you can figure out what you have in the XY plane. It's either a parabola, which you would get if A was 0 or C is 0, but the other non-zero, okay? I'm not addressing that in this model. Or if A and C are both non-zero, you get something like this. Again, could be there's no solution. If A and C are both positive and gamma turns out to be negative, you have no solution, okay? Otherwise, you either get an ellipse or one of the two possible hyperbolas. That just depends. If the hyperbola, it depends on which one of these is positive and which one is negative. If both positive and this is positive, you get the ellipse. Okay, so what you have down here in the XY plane, you can sketch this rectangle. Now, I don't know how experienced you are at sketching in 3 dimensions, but I'm going to kind of show you. Okay. I'm going to want to go through this point and this point. This is X and this is Y. Okay. Then I have equal and opposite X values on the X axis, because that's what we have here. Okay. And I have then equal and opposite values on the Y axis. And I make these tick marks here parallel to the X axis. If I'm drawing it in 3 dimensions, then I've got to have some sort of orientation, okay? And lines perpendicular to the Y-axis go this way. They don't look perpendicular, but they kind of do when you're used to looking at 3-dimensional diagrams. So what I can do is I can draw a dotted line through this, parallel to the Y-axis. Because for those lines, X would be constant. And then I can draw lines parallel to the X-axis, because that's where Y is constant. And now I've got a rectangle I can use to sketch the ellipse or hyperbola. So I'll draw the asymptotes in case we have a hyperbola. And now I can sketch my ellipse. When I sketch the ellipse, remember I start here and go parallel to this side. So I start off in this direction, but then when I get here, I've got to be moving in this direction, okay? So I'm always going to start out parallel. I want to do it. It gets a little tricky over here, okay? I never get that right. It looks something like this. Right there's your ellipse in the XY plane. Okay. No, it's not an ellipse then. And again, if A and C are both non-zero, then it's either going to be a hyperbola or nothing. If gamma is 0, that means you have the point at the origin. If gamma is negative, it means you got nothing. Okay. You might think about that, but it's fairly obvious. Okay, well, I can draw my 2 possible hyperbolas, one here and one here. One. That's pretty badly drawn, but there it is. One here. Then like so. All right. kind of makes sense? Can you visualize that in the XY plane? Can you visualize what it would be if it was a hyperbola opening in the positive X direction? I mean, you just got to ignore the ellipse and the other hyperbola. It's going to be the orange hyperbola, right? So just kind of pretend the others aren't there. The orange hyperbola, that would be it. Yeah, that's just not very well drawn, actually. But, or if it's the green hyperbola, not hard to decide which one it is, if it is hyperbola. Okay. Then see what it is. See ellipse, that's pretty easy. Okay. Okay, now. You could do the same thing in the XZ plane, right? And in the XZ plane, it could again be an ellipse, a hyperbola, or parabola. So you could have ellipses in this plane and hyperbolas in this plane. Okay? Or some combination thereof. And then that would kind of determine what you have in the YZ plane. Maybe it's an ellipse, maybe it's hyperbola, maybe it's even a parabola. Okay, you could have maybe all three on the same graph. And how do you put it together? How do you visualize it? And how do you sketch it? Unfortunately, WebAssign doesn't actually ask you to sketch anything, it just asks you to recognize sketches. So it's a lot easier to recognize a sketch than to understand the quadratic surface and be able to sketch it, to be able to visualize it without somebody showing you the picture. Okay? But I think it's important to be able to do that because multivariable calculus doesn't absolutely require, but is much richer if you're good at visualizing and thinking in 3 dimensions. So I kind of emphasize being able to sketch these. Used to be before, days before WebAssign, that's what we did. And people learned it much better than they do by just being able to recognize it when they see it. So I urge you to, and I'm of course going to ask you to sketch some of these. Okay? Some of the simpler ones, there's some of them that are pretty hard to sketch. You don't know how to shade them, it's a mess. Okay, well, it could be. Now, okay, well, let's just say, okay, now let's let Z equal 1. Okay. The plane Z equals 1. Where's the plane Z equals 1? Well, this is the plane Z equals 0. What I've just sketched is all in the XY plane. That's where Z is 0, right? If Z is 1, let's just say Z equals 1 here. Okay. I like to clutter things up. Okay, Z equals 1 here. With that, we can draw an auxiliary x-axis, call that x prime, and a y-axis parallel. Sorry, this is a y-axis, call that y prime, parallel to the y-axis. An x prime axis parallel to the x-axis, but 1 unit higher. It should have been more parallel. Kind of messed that up. And then when we do all this stuff, if Z equals 1, that's going to change the value of this gamma, isn't it? Because if Z equals 1, then if Z equals 0, all we got here is G, and then we just subtract off whatever we have to add here and here to complete the square, and that gives us our gamma. Okay. So let's say that gamma gets smaller. No, sorry. Let's say that gamma gets bigger. Okay. What's that going to do to this picture? Well, if gamma gets bigger, so does this rectangle, doesn't it? Okay. Okay, well. A and C are still gonna be what they always were. Of course, that means gamma over A is gonna get bigger and gamma over C is gonna get bigger. That's why the rectangle gets bigger. That's the square root. Square roots get bigger. So let's say the rectangle gets bigger so that it intersects out here and out here and back here. It's gonna be a little hard to see, but in here, let me sketch the auxiliary axis. Slightly different color so we can. Whoa, I kind of lost it there. Okay, well, here's our prime axis. Where? Okay, now a rectangle gets bigger in both directions proportionally. So our intersections are going to be like here. We can sketch a light line here, and a light line here, and a light line here, and a line through here. And we kind of lose some of it over here. But we can see that, for example, if this is an ellipse, which would be the easiest thing to see, I'll just draw that in white. This is going to be a bigger ellipse. Where is it? Coming around to here. And around to here. Okay. That makes sense. So what's happening as we go up is these ellipses get bigger. Now, maybe they get bigger in a parabolic fashion like this. Maybe you get hyperbolas attached onto at every point. Okay. So there's a hyperbola like between here and here. Vertical hyperbola. And here. And out here, who knows? Could be any combination of things. Now, it does help to look at pictures. You want to look at the different pictures and get the different classifications. But a couple of possibilities. You've got ellipses. In this plane. And trying to give myself a little bit of but you get the idea. Ellipse here, right? Maybe even a circle in each place. Maybe the ellipse is longer in this direction or longer in that direction. Okay. And maybe then what you have is hyperbolas here in the vertical. So that at each point here, and each point down here, you can sketch an ellipse. And you start to see kind of what it might look like. Does that make sense? Can you kind of visualize that? It's like just a surface of revolution. You rotate this curve this way, but it's not a perfect revolution because you're rotating it along so that each hyperbola stays in contact with these ellipses. Okay. So that you can even, okay, top's open. Down here we have one of these. Down here we have this. 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 And down here we've got this. And then you can kind of scan. The purple is there, and you start getting something that you sort of visualize. That makes sense. So let's do this one example. Let's see what happens with the numbers. Okay. Now, am I out of board space? Okay, I am. So I'm gonna have to wash a little bit of board. This is one that I will have. So I'm gonna write down an equation. And have you work a little sum. I'll clear a board so we can work it out. But it's gonna be pretty simple. First of all, I'm gonna eliminate A, B, and M. So I'm gonna say f of x, y, z equals okay. Now what I want. Okay. That might work. So what do you end up with in the XY plane? Or what about the YZ plane? Or the XZ plane? What do you have there? Remember in the XZ plane, Y is zero, and the XY plane Z is zero, and all that stuff. And I'll get some boards clean. Okay, well, hopefully everybody makes some progress. And I said that this equals zero. Here's your f of xy function. And if we set f of xyz equal to zero, then we can actually simplify this. So what we get very straightforward. First of all, we add 1440 to both sides. So we get, now, 4 goes into 1440, 360 times. Yeah. I worked it out, so we have sort of nice round numbers, okay? Unfortunately, I think I got my arithmetic right. So I honestly divided the, think it might be right, okay? Now, I'm using A, B, and C differently than I did in this formulation, because we haven't really used the letters A, B, and C. We don't really need to. Just follow what I did here. What's A? Well, A squared is 360, so A equals 6 times the square root of 10. B equals 4 times the square root of 10. C equals 3 times the square root of 10. Right? I mean, if this is A squared, it's 360 squared. 360 is A squared, so A is the square root of 360, which is square root of 36 times 10, which is 6 times the square root of 10. Okay, and similarly on these. So these are in the ratio of 6 to 4 to 3. Okay, now let's just look in the XY plane. You have x squared over 6 square root of 10 squared minus y squared over 4 square root of 10 squared equals 1. Well, this is x and this is y. Then in the x direction, you got 6 square root of 10 and minus 6 square root of 10. In other words, well, you have a rectangle. Okay? And it's 6 square root of 10 here, 4 square root of 10 here. So total length is 12 square root of 10, total height 8 square root of 10. Okay, so that's easy. And now we know we have what? We have a hyperbola. Because this thing is negative. So we're going to construct a hyperbola. And what is it that can't equal 0? Y can certainly equal 0 because you'd have a positive equal to 1. But x can't be because you'd have a negative equal to 1. Since x can't be 0, then your parabola has to be here. Sorry, my parabola has to be here. So there we are in the XY plane. And you can sketch that. And let's go ahead. I'll use colors just because I really want to confuse things. Didn't trace this very well. She take that one all out, but this is really terrible. Yeah. Just fix it a little bit. I think it's a little better there, but not great. Okay. So fairly easy, right? Yeah, you got to practice it. You got to learn to draw these. But not overly difficult. Okay. In the YZ plane, you got y squared over 4 times square root of 10 squared, that's negative, plus c squared over 2 square root of 10, 3 square root of 3. It's 3 square root of 10, then 3 square root of 3. Okay. Well, YZ in the YZ plane, We'll do that one in blue. Here's Y, here's Z. So the YZ plane, of course, you're gonna get well, your rectangle. It's 4 square root of 10, 3 square root of 10, and your hyperbola, since you have opposite signs, Z can't equal 0. So Y can equal 0. Is that right? Yeah. So Y can equal 0. So, sorry. Y can equal 0, which gives you a Z. So that gives you the hyperbola here. Looks like I didn't do something wrong here. I screwed this one up. No, Y 0 here. Y 0 everywhere in the Y axis. I drew that wrong. Hyperbola in the wrong place. It opens on the X axis. And I've got it intersecting the Y axis. And I never did that. Be careful like I'm not. Okay. Anyhow, our asymptotes are here. So we come out like this. Here we come around like so. Okay. There's our hyperbola in the XY plane. And now, in the YZ plane, a rectangle intersects this one on the Y axis. Because of course, we still have Y equals 4 square root of 10 here, which is what we had here in this rectangle because of this. And the orientation of these things is always weird, so you gotta be careful about that. But let's just say there's our rectangle. The YZ plane, so I'm gonna make it look like this. Now, does it look like these rectangles are at right angles? It look like this one's in the XY plane and this one's in the YZ plane? It's like you rotate this one up and you get this one. Hopefully it looks like that. Then the thing intersects the Z axis. So that this hyperbola, draw my asymptotes. This hyperbola goes off like so. And like so. It's a little hard to see it. If we then do the XZ plane, we have a third rectangle, which is going to intersect the X-axis . same point where this one intersects. These things are overlapping in a weird way. And that's not necessarily good. And the Z plane. So it's gonna look something like this. So now we've got three rectangles, one flat, one vertical, and one here. And they all intersect at the origin. I mean, the insides, planes all intersect in the origin. And we have an ellipse for this one. A little hard to see from the picture what points are common to these hyperbolas, but you can work that out. I want to see if you can do a better job than I did on that picture. Okay. See where you think they are, see how you can make sense of the picture. Don't expect miracles. And most of the sections you see in your text are going to be like this. I don't think you're going to see much where you got to worry about the translation. I think most of these things are going to be centered at the origin. If I wanted to translate this thing, now let's say I took this thing, whatever it looks like, and wanted to move it over 5 units in the Y direction, up 4 units in the Z direction, and -6 units in the X direction. Well, I just replace X by X plus 6, Y by, what was Y minus 5, and Z by Z minus whatever. Okay. And then, of course, I'd end up with something that looks like this. If I expanded it, and I'd have a different number for G. And I'd have numbers for B and D and the last one. Okay. But right there's the overview. You want to look at these things. And usually it's best not to try to look at it in 3 different dimensions. You want to look at it kind of like we did. Where to go? Yeah. Okay. You get a better picture if you just think stacking them in the Z direction or stacking them in the Y or X direction, whichever works better. And then you have the same shape everywhere. And you see you get a hyperbola this way in the YZ plane, and you get a hyperbola in the XZ plane. That's totally consistent with the numbers we have there. Okay. And ellipses in planes parallel to the XY plane. And then we see the ellipses get bigger as you move away from the XY plane. So maybe it looks like this. Make sense? You see plenty of pictures. Okay. Gotta go where you can. Okay, so what you end up with here is you have ellipses parallel to the XZ plane because X and Z have coefficients of the same sign, right? And this number over here is positive. That's enough to tell you. Yeah, I mean, if the number over here was negative, we wouldn't have anything. It wouldn't even hit the XZ plane. It would hit a plane up here somewhere. So what you have is ellipses that get bigger and bigger going this way. So it looks a whole lot like this one, but turn on its side. Okay. Now you can also think in terms of the XY plane. In the XY plane, you get hyperbolas. What happens to the square the hyperbola goes in? Just get bigger and bigger. Okay. So you can look at it in many different ways. And generally you choose one plane and then cut it with planes parallel to that one. And then think about, okay, what is it in this plane or what is it in that plane? Is that consistent with what I get when I try to picture it? It's an art. Practice it, learn to at least look at the pictures, but also work on being able to sketch them, because I will ask you to do that on the test. Okay? And I don't know if you can see anything here. Since you saw, everything went out of focus when we started moving stuff. There's better. Okay. Okay. Everybody just let, one thing I'll add. If it's an ellipse in the XY plane, then it's an ellipse in every other plane, except maybe for some planes where it doesn't exist because you got a negative on the other side. You got, and similarly, if it's an ellipse in the XZ plane, then it's ellipses all the way out. And if you know then what happens in the XZ plane, and also what happens in the XY plane, you can see that these ellipses have to follow, these ellipses have to intersect these hyperbolas, and gives you it gives you a three-dimensional picture. You've got to work on it. But think of how the ellipses stack this way, or how the hyperbolas stack as you go up or down, and how all that works together. Okay.